So that's what we're going to be discussing today. If you have your book, it's on page 128. You don't have to worry, but I'm just telling you where it is. Okay? We've discussed this even in polynomial. Do you remember I mentioned something about every polynomial of degree, in complex numbers? I just gave you hints during complex number class. So I'm just going to write as it is in our book. Okay? It states that if p of x is a polynomial of degree n, then p of x has n roots, each of which can be written in the form a plus bi, and some will be repeated. Let's just say every polynomial. Let's just write every polynomial of degree, or any polynomial, it doesn't matter, of degree n has n roots. Okay? The roots could be complex, n zeros actually. Instead of saying root, or polynomial equation will be root. Okay, what I mean? Okay. As n zeros. That's basically what it says. So if your function is cubic, you're expecting 3 answers when you solve it. If it is power 4, you expect 4 answers. Okay? But these are some things that we need to take note of. Of course, some of these may be repeated as n root, some of which may be repeated. Remember, we said zeros. We never said real zeros or complex zeros. Okay? So, if there is no specification, just take them as complex. Because even complex is a superset of the real. Do you agree with what I mean? So every real number is a complex number. But not every complex number is a real number. Hello? Leo, does that make sense? Every root will be in the form a plus ib, for example. So if b is equal to 0, then it becomes just a real number. But if b is not 0, then it becomes a complex number. But this is what every 0 will look like. And if it's a polynomial equation, the theorem is about the roots in that case. Okay, so I'm just taking it as a function. So quickly, we have the following properties if the polynomial is real polynomial. So I need you to take note of these properties. One, p of x can be factored into n linear factors, n complex linear factors. We're using the word complex here to generalize a plus ib. So, of course, real is part of this. Okay? That's one. Second observation. I'm taking this from your page 129, but I need us to put it in our notes. Every polynomial can be expressed as a product of real and some real irreducible quadratic. It's possible when you're factorizing, you'll come across a quadratic part that cannot be factorized. That's what we mean by irreducible quadratic. So P of x can be factorized into some real, linear, and real irreducible quadratic factors. Of course, what do we mean by irreducible quadratic factors? When the determinant is less than 0. So you have a function that is power. If you have a power 4, you have maybe x plus a, x plus b. Unfortunately, you can only have maybe cx squared plus dx plus e. And in this case, this cannot be factorized. Because the discriminant, d squared minus 4c is less than 0. This is what we're talking about. So is either you are able to factorize it to all linears, or maybe you have some linears, but you get stuck with some quadratic that you cannot factorize. That's the second point. Third point. We already talked about the third point, so I'm not going to repeat that. The third point here is every polynomial has n roots, some of which may be repeated. So that is the fundamental theorem of algebra. We'll not repeat that. So the next important point if P plus IQ, or maybe we'll call it QI, doesn't matter. Okay. This time around, Q is non-zero, which means if we have a complex number. If a complex number happens to be one of the zeros, the conjugate is also a zero of the polynomial. Okay. It's a zero of P of x. Then, remember P of x is a real polynomial, so I'm not going to keep repeating that. Then its conjugate, P minus Qi, is also a zero of P of x. This is very, very important. This in particular we are going to apply in various questions today. Finally, every P of x of, or should I say, if n is odd, remember n is the degree, okay? If n is odd, then P of x has at least one real zero. At least one real zero. These are very, very important for what we want to do. Let's get right to it. We'll take some questions from the exercise. You can study the example later. So I'll take this from exercise 5H. It's on page 129. So I'm going to skip number 1. Let's go to number 3, maybe. Let's go to number 3. P of x is a real cubic polynomial. Do I have your attention? P of x is a real cubic polynomial for which, let's write the important points, for which P1 equals P2 plus I equals 0 and P of 0 equals negative 20. That's the information we have. The question is find Px in expanded form. Find Px in expanded form. This. focus please. P of x is a real cubic polynomial. All these properties work for real cubic polynomials. Okay? First one is trivial. We've talked about that, before. We don't need to waste that. Second is also clear to most of us, right? Everybody should understand. The third one is probably what is new. And we actually came across this when doing De Moivre's theorem to find the nth roots of complex numbers. You will notice that for some odd numbers, the power will be conjugate, something like that. Do you remember? So we came across this, but I didn't say more because we will still talk about it in Fundamental Theorem of Algebra. So what this is saying is that if, remember, when anytime I say P of x, I'm referring to a real polynomial. Do you remember what a real polynomial is? What do we mean when we keep saying real polynomial, real polynomial? What does that even mean?
No I.
Say that?
No I.
Wait.
No imaginary numbers.
Say that again?
No imaginary numbers.
Where?
The expression.
You're not being concrete. You have an idea, yes? The coefficients are all real numbers. But when you say no imaginary in the polynomial, what do you mean? Okay, if the coefficients are all real numbers, then it's a real polynomial. If you have a polynomial where you have ax squared plus bix plus c, this is not a real polynomial. As you can see, the coefficient of the second term is a complex number. Okay? So all the polynomials we'll be dealing with are all real polynomials, basically. So if you have a real polynomial, if a complex number is a 0, the conjugate of that complex number is also a 0. Does that make sense? If a complex number is a 0, you know what conjugate is, right? The conjugate is automatically a 0. And this says that if the degree of the polynomial is odd, okay, there is at least one 0. This is trivial. Remember cubic function in graph. What do you notice about what can you say about a cubic function that is not necessarily happening in